In this video, we're going to talk about the SN1 reaction mechanism. So in this case, we have this hydrocarbon chain right here, which is attached to bromine, which is a halogen, and it's in a solution of potassium iodide. Now, potassium is the positive ion. It's really going to be a spectator in this reaction. It's not going to do much. The iodide ion is going to be the important thing. It's going to be the nucleophile. So initially what happens is that this bromine attached to this tertiary carbon is going to leave. So these electrons in the bond are going to join bromine, and then bromine is just going to separate as a negative ion. So it's going to turn into bromide. And what you're going to get is a tertiary carbocation. This carbon right here is attached to 3 other carbons, and it's positively charged because it just lost the bromine plus all the electrons in that bond. Then what is going to happen is that the iodide ion is going to come in and attack that carbocation. And then what's going to happen is that it's going to bond with that carbon, and your final product is going to be looking similar to the one you had before, except the bromine is replaced by the iodine. So the halogen that is initially there is going to be replaced by the nucleophile, in this case the iodine. What you need to understand about the difference between this and the SN2 reaction is in the SN2 reaction, this entire thing happens in one step. Meanwhile, in the SN1 reaction, there's a carbocation stage that happens. Now, let's draw the energy diagram for the reaction we just looked at. We really only have 2 transition states, so we only need to draw 2 of these. Draw it better, actually. There. Draw 2 of those. Initially, we had the carbon chain attached to the halogen, which was the bromine, and then we had the carbon chain had a carbocation. Then at the end, we had the carbon chain attached to the nucleophile. Now, the SN1 reaction, the rate of it depends on a constant times the concentration of the substrate, and that's has an exponent of 1. So the substrate is doubled, the rate is doubled, the substrate is quadrupled, the rate is quadrupled, the substrate is tripled, the rate is tripled, so on and so forth. Now let's talk about this next example. And this is going to react with water. Now, in this case, the water itself is going to be the nucleophile. That can happen. And I'll explain the mechanism, but whenever you have the solvent being also the nucleophile, this is called solvolysis. So, as we talked about initially, what's going to happen is that these electrons are going to join bromine, and you're going to form a carbocation. So you have this tertiary carbocation right here. And then what's going to happen is that the nucleophile, which is the water, and the way water is a nucleophile is that the oxygen is attached to 2 hydrogens. However, the oxygen is more electronegative than the hydrogen, so it's going to pull these electrons a little more toward itself, and the oxygen is going to bear a partial negative charge, and the hydrogens are going to have a partial positive charge. And this partial negative charge, the oxygen, attracts it to the carbocation. And so the oxygen is going to attack the carbocation, and in the next stage of the reaction, we are going to have a situation where the water is going to attach to the carbon. However, the water is going to have a partial positive charge at this point. What happens next, let me just move everything up, is that we're going to need another electrophile, another water molecule is going to come over here. And because this water molecule is partially negative, it is going to be attracted to the partial, not really the partial, the full positiveness of this oxygen atom, and not just the oxygen atom, this whole area right here is going to be positive. What this oxygen atom is going to do is it's going to steal a hydrogen from this oxygen. And this stage is called depronation. Hydrogen has one proton, so when you depronate it, you take away a proton. So the electrons in the bond are going to go toward the oxygen, and then the hydrogen is going to go toward the outside oxygen. And what you're going to have is, if we have enough space, you have enough space. You're going to have depronation, and at the end you're going to get an OH, and then you're going to get an oxygen with 3 hydrogens, which is a positive charge. Now let's talk about minor and major products. We already know that this is going to be the major product, or not really the major product, the main product here. But when this oxygen wants to attack the carb cation, if it wants to attack it from the back, there's no barrier, there's nothing here. However, remember that when the bromine got off, the bromine itself turned into a negative ion. If the water wants to attack the carb cation from the front, it's going to hit the repelling force of the bromine. Since the oxygen is negatively charged partially, it's going to be repelled by the negative charge of the bromine. So it's going to have a hard time approaching the carbocation from the direction which the bromine came from. So in this situation, the major product is actually going to be the inversion and not the retention, which means that if we had a wedge initially, more of our products are going to have a dash, which would mean that the water came from the front, or really came from the back and not from the front. So this is going to be the major product, and it's going to be the minor product. Now, let's go over the energy diagram for the reaction we just went over. In this time, we have 3 transition states. We have transition state 1, transition state 2, and transition state 3. Because we had 3 stages in our reaction. At first, we had the carbon chain attached to the halogen, which was bromine. And then we had the carbocation for one moment. Then we had the carbon chain attached to the water molecule with 2 hydrogens, which had a partial positive charge still. And then at the end of depronation, which was one of these hydrogens going away, we had the carbon chain attached to an OH, which is also known as an alcohol group. And this is going to be the energy, and this is going to be the reaction.